Ladies and gentlemen, Monday, 31st of January, and we are here for the EPIC meeting on UV disinfection. So I really welcome all the panelists and all the participants to this interesting meeting. And I would like to start sharing a very short intro. So, as I said, today we will speak about UV disinfection. This is a quite hot topic, but this is just one of the calendar that we prepared from now until June. We already did last week, 2 weeks ago, another meeting about thin film materials. Then we will touch a lot of other topics: quantum computing, automotive lighting, agri-photonics, LiDAR, co-packaged optics, VCSELs, and what else? How we do it? We do it with the great support of the EPIC team. The EPIC team that is helping us to discuss about technology, to provide unique market reports to our network, to make networking with all the members and the people of this environment, helping members to access to the markets, and also supporting them with mentorship programs, supporting you in the search of skilled operators for these technologies, and also, why not, supporting them when they are looking for investment at different levels. As I said, we are serving a community that is growing day by day. This slide is already old because
Antonio, sorry, but you are not sharing the slides.
Not sharing the slide. Okay.
No, we don't see the slides. Yes, now it's okay.
Now, okay, restart. Sorry, but we are on live. So we start here from the TEPI, from the EPIC team. So the EPIC team is really a great team that is supporting all the members on technology, market reports, networking, access to the markets, mentorship program, support in job for photonics skills, and investment. We are more than 700 members. Now we are around 750, 760. And this is the community that we serve. We are really proud to serve this large community. Do you want to be in touch with any participant of today? Very easy. Send an email to us, to Ivan Nikitski, and to myself. And we are really happy to connect and to introduce to anybody that is joining the meeting. Moreover, you will find this meeting online on our YouTube channel as well on our website. And then we go to the meeting of today. So online technology meeting on UV disinfection. Clearly, in the last period, UV disinfection is becoming, unfortunately, a little too famous. But in any case, UV disinfection is impacting a lot of business and industries. So we will learn how it is relevant for the specific time, but also how it could be is relevant also for other industries. And which are the current challenges and which are the current trend of this application. The agenda will be, the meeting will be moderated by myself and my new colleague, Ivan Nikitski, that I really welcome. And then we will have 6 key speakers. Peter Gordon from CudoForm, Jörg Söllner from USHIO Germany, Nicolas Volet from UV Medico, Olga Stroh-Vasenev from Laser Components, Arthur Kreitenberg from Dane, and Dane Rönnholm from Intellego Technologies. From these 6 ladies and gentlemen, we will learn and we will follow the evolution of these technologies. But this probably is the most interesting slide. These are the company that registered today. And as you can see, here we have really the full spectrum of the stakeholders. we have several companies, several end users of these technologies on different segments. As well, we have all the value chain, lighting solution, UV LEDs, laser sourcing system integrators that are really the bridge between the components and the end users. As well, a lot of other elements that are necessary, materials, added value distribution, manufacturing and testing equipment, and so on. So at this point, I stop sharing, and I'm really proud and glad to introduce the first speaker. So please, Gordon, go ahead and tell us what is coming from your side.
Hi, can you see my screen?
In this moment, no.
Well, it says end of the slideshow, so I can just say thank you very much for your talk.
All right, so let me
Just need to go set it up.
let me go set it up a second time. You should be able to see the first slide.
There it is. Make it in full show. No, it just says end. I think.
Okay, so I will stop sharing and I'll just do it this way.
Okay.
No problem.
I know that you did a bit to solve also my problem. So we are both.
Yes. That's okay.
Yeah, we can
Now
see
we
that.
are. Please go to
All
the
right,
presentation
so-
mode.
Thank you. All right, so I'm going to keep it here because then I don't have a problem. It's all right. You can see split screen. I'll just lead you through it for 6 quick slides. Thank you, Antonio. Thank you, Epic. Thank you, my colleagues. Some are reconnecting after, I think, 2 years. The theme of Epic is always collaboration and partnerships and driving innovation forward and producing good solutions. So to support that theme, I have a couple great slides for you. And as you saw in the big segregation of all the different companies, we're components, photonics components, micro-optics company. Let me show you a little bit about what we're doing in the UVC LED space. So here we are. I'll highlight a couple keywords. We make metallic optical components. We make them in Camarillo, California, near Los Angeles, based upon a very proprietary technique. And fundamentally, they're used as sort of a light path, confinement, concentration, manipulation, collimation capability to improve optical performance of solutions. And typically, our intervention lowers assembly and test costs for the end user. So we take a lot of money and time, particularly in the fiber optic space and alignment, out of the process of making an end product. Here's a little bit of what we work with. So we work with metals. Metals are a unique optical component. We make them very thin. We can solder them onto boards, very important for fiber optic communications. They're platable, they're rigid, and again, very thermally conductive, very thermally matched to silicon. So as you see, we're very fiber optics oriented here. We make them very reflective, so they're freeform optics, typically asymmetric mirrors. We do beam and spot shaping, confinement and concentration. We can redirect beams. We can expand beams. We can manage divergence, particularly of slow and fast axis within a laser diode. And you don't have to do any additional processing. So that means that these mirrors are particularly smooth and accurate and fast to market, right? So our customer base likes that. It's a scalable manufacturing capability, and it doesn't include secondary processing steps. So it saves a lot of money for everyone involved. We do a lot of accurate shapes and locations. Again, here's a cabled co-packaged optic for high-speed data links. We're operating in the 51 terabit per second realm now for data centers. And we add a very interesting capability to align the fiber optics to the sources. So you get a pretty good idea what the capabilities of the metal are. And let's see how they apply to the topic today, which is enhancing UV disinfection. So here's a really busy slide, but it shows a lot of good takeaways. We just presented in the UVC LED track at SPIE Photonics West. Actually, this went virtual, but it's in the public domain now. And what we did in the spirit of collaboration and partnership, we worked with NIST, Cameron Milner, and Eugene, Zhang, his engineer. I think we were the first IUVA member to actually co-publish a technical document. It will be in the SPE proceedings. And we used their newly up and running UVC LED measurement and calibration lab. And we actually went through the steps of coupling this highly reflective micro optic to a UVC LED emitter. And as you move sort of left to right column, you can see sort of how we couple to a UVC LED, how we actually have very good metrology. So it's very smooth surface. There's measurement and metrology metrics that we apply to this, that we apply to our fiber optic components. We actually show before and after beam shaping, and we have some simulations that we've done. We did some coupling to fiber optics to really look at the spot size and its confinement. And then we sent him over to Cameron's lab in Gaithersburg, and he did all the experimental validation. He has a very sophisticated lab setup, and did all the measurements, given the outputs as a baseline of the LED, and then with our optics. And the key takeaway of all this slide is the similarity between our agreement, right? We did optical simulations. We're an optics company, and his measurements. So the key word here is that if the beam is, if we say it's simulated, the beam will look like this in the far field, it's going to look like that because NIST, in a sense, demonstrated it. So very interesting work, and this is available now to the public. So how do we sort of take this great science, this engineering, this micro-optics, and apply it to today's discussion? So just like the LED suppliers who grow their LEDs and MOCVD reactors, we can pick priority knobs now too of how to use the LEDs, right? We dial in what the priority is for a solution. So we now work with OEMs, and a lot of interesting new designs are coming online in various applications, and they really want to fine tune what's happening in the far field, the irradiance, right? They want to control that. They may want to control costs, or they may want to have something aesthetically interesting, a fixture that looks great. They want to pattern a certain target, could be a coil and a handler. They want to control dose. They want to control the patterning of the radiation and the projection. Talked about this a couple of years ago. And ultimately, and I think this is the theme of everyone's talk today, you want to sort of boost efficacy. You want to sort of increase the margin of safety. You want to make it usable for professional and industrial applications. And in one area, we want to ease UL certification. We want products to go through our colleagues at UL with no hiccups, and the optics and the photobiology work well, and people get products to market. And then the user base is able to secure and promote a healthy environment in facilities, or in water treatment, or in hospitals. So let's look at a little bit of the contours. This is getting kind of interesting. So we took a really single 50 milliwatt UVC LED, sort of low power now for UVC LEDs. I think we'll talk a little bit about that later. And we extended the reach in the x-axis, right? So the top is something that has a micro optic, little device that I showed before, and then the bottom half is without the micro optic. You can see the optical reach, and a fairly substantial irradiance moves to almost 2 meters away from the LED. Whereas without the micro optic, you sort of get a lot of irradiance very close to the lens of the device, but it doesn't go very far. That has some applications, but typically people are looking to get the most photons to go to where they want to go with it, and beat the inverse square law, right? You don't want to fade out very close to the LED. You want to get a lot more optical reach out of it. And the key here is, I didn't show the y-axis because it's a little proprietary, but let's say there's no divergence in the y-axis. So now you have a sheet of light, right? It's all going out in the x-axis, and there's very little up or down, right? It's all, the divergence is very, very small in the y-axis. So that has implications for a few interesting applications, but I wanted to sort of change speed here and do what I don't think people have done before. I actually made the invisible now visible, right? So we took that irradiance pattern and we colorized it, right? So here are actually 50 milliwatt UVC LEDs, and they do in space what we simulate they do in space. You can actually now colorize these. We happen to produce a red color out of a invisible UVC optical radiation emitter, and it does exactly as claimed by the simulations. The top is optical reach is very far. The bottom, it sort of fades out very close to the diode, right? So this has interesting implications, right? Because now you can see in space, whatever that space is, air or a hospital room impinging upon a surface or within a water pipe, where the actual optical radiation is going. It has phenomenal design and also use implications for really clarifying what we say is happening, but now it's visible. So here's a little bit of a placeholder rendition, because this is kind of the secret sauce to where we're taking this capability. So I just showed that we can colorize the contour lines in a horizontal plane, right? So we applied our micro optics to a UVC LED, and we've coupled different micro optic configurations to many different vendors of UVC LEDs. It all comes up the same. It gets calibrated, right? We can measure it. We know that, it's sort of mistraceable now in a sense, because it works as claimed. And now we can actually use different colors and colorize the actual radiance fields in space. And if you just have a stop clock, right, now you have dose that's been colorized by this technique, right? So you know exactly what dose is happening where in space. That's pretty slick innovation in the dosimeter area, for example. So we visualize, we validate, right? And we can reconfirm now. We've done this with a couple interesting configurations. It's very accurate, right? Because the calibration says that we match, simulation matches measurement. And it's really repeatable, right? It's repeatable and repeatable. You can keep doing this and you always come up with the same colorization, right? And that means you can always say, wow, it may, here's the design, here is the initial installation, and it actually works as claimed, right? And then we can do feedback. Let's say something changed in the operating environment, right? One can imagine, I think Olga is going to talk about this, what happens with changing UVT in a point of entry or point of use water pipe. Let's say something happens. You can look at the irradiance pattern and make an adjustment saying, oh, we have to make an adjustment. The water quality's changed. And then you now have a new visualization to match the changing operating environment. So that's a lot in 4, 5, 6 slides. I think I met my criteria of 6 minutes. So thank you to the audience. Thank you to Epic. Thank you to my colleagues. I'm not quite sure how we work Q&A from here, but you can certainly contact me. And I'll stop sharing.
Thank you so much, Peter. Really, we started really hard. And I know from my colleague Ivan that also we have some question already coming in the chat. So Ivan, what?
That's correct, Peter. So Olga, one of our speakers today from Laser Components, is curious if this technology is applicable in the mass production stage of the UV LEDs.
The micro optics are currently in mass production, yes. So we've tooled, we can ongoing tool the actual micro optic, right? We can stamp millions of units a year. And that actually derives from our other applications, right? Think about how many data center fiber optic links are going to be implemented in 2022. And we also operate in LiDAR, near to eye, and clinic on a wrist. Those are really high volume applications. So yes, the micro optic is in production, and the UVC LEDs are in production. So it's a great marriage of optics and emitters right now. Thank you for the question.
Okay, thank you so much. I saw also one hand raising. I'm not sure if it is Ruth. You raised the hands, or it was a mistake from my side?
Well, in the meantime, there is one more question from Lumenos. Robert de Jonge is curious if there is any feedback on the reliability data in these optics.
That's another good question. So there was a small little segment of that SPIE paper, and that was metrology. So yes, because of Telcordia standards for fiber optics, we test the micro optics to 85 testing. So really rigorous packaging capabilities. So they withstand that operating environment. So that's implications for our industry, right? Like particularly automotive and maybe life science applications. But also, how does the optic hold up to continuous optical radiation, and the surface doesn't get affected? It's honestly, it's much more robust than the emitters, right? It will outlast the LEDs with respect to reflectance, which is about 90%. We can make it up to 95% over thousands of hours of continuous use. So good question, very reliable. That's not the weak link in system reliability. Actually boosts reliability. If you look at my my little chart, right? You can underdrive the LEDs, but get more photons out. So you get a little more lifetime out of your LEDs. Good question, thanks.
Okay, okay. And then maybe I make just, let's say, the general questions. I would say the typical EPIC question. So, Peter, what you think, what you are looking for from the other colleagues of this environment, and also how you are open to cooperate with them and what you offer to them?
Yeah, so I think we'll answer the second question first. So we have a lot of relationships in this ecosystem with the UVC LED manufacturers. Makes a lot of sense. Everyone has a different source file coming out of their emitter. We have to form the optic to confine and concentrate that output, those rays, right? So we have very good cooperation. And what I like to see there is that go to sort of sub-assemblies that really help the solution designers, right? So that's an epic thing. You get the LED makers and the optics makers to work together to help the solution providers. On the solution provider side, I think it opens up an innovative and creativity path, right? So now they can start envisioning maybe some interesting water, air, surface capabilities at the sub-assembly or final product that can utilize sort of this interesting new optical capability, and also utilize this interesting visualization capability, right? So it's really for designers. So we're very open. I've been in the industry a long time. I know a lot of the OEMs, and we already have some working relationships. We're very receptive to the audience today, some of the speakers, to help them create better designs that are more efficacious, that are safer, that, as I said, could go through UL and other regulatory or certification exercises a little easier, right? So we get the solutions out to the market. They're industrial, they're professional, and the users' claims match. Their claims are sound, right? Because now they can show that their radiance patterns are real. But thank you. Yeah, that's the spirit of EPIC, that cooperation. Thank you.
Okay, thank you to you, Peter. So, any other question to Peter? I think that maybe we move on because it's really a dense agenda today. So the next speaker is Jörg from USHIO. So we are already dealing with designing and about the UV sources. So we go deeper in this topic, going to a manufacturing of UV sources. Please, Jörg, the floor is yours.
Okay, thank you, Antonio. Just a moment, I try to share my screen. I hope you can see it.
Yes, great.
Okay, thanks. So my name is Jörg Söllner, and I'm with USHIO Germany and located in Germany. And my topic of my talk is today the USHIO Care 222 technology, the filtered far UVC disinfection. Now I try to switch the slide. Okay. Well known already today is that UVC light can efficiently inactivate microbes such as bacteria, virus, and so on, which is a very hot topic right now. And the mechanism, as you know, is that DNA and RNA of the microbes absorb UVC light and breaks the bonds, and by this inactivates the microbes. And the typical type of lamp you are using is the conventional germicidal lamp, a low pressure mercury lamp at 254 nanometers, which is rather cheap. But the big disadvantage is, of course, because of the 255 nanometers, This lamp causes cancer and cataracts when people are present. So what you can do with these lamps, of course, is typically in the night you can disinfect the room in your office, and when people are coming in, then you have to switch off, and in the night you can use it again. So, but during the time people are present in the room, the air and the surfaces cannot be disinfected. So let's have a look on the skin of a human. Here's a cross-sectional view. You can see UVA light is coming very deeply into the skin and penetrating into the epidermal layer, so the living cells. UVB light as well, and 254 nanometer light, UVC light, still coming into the epidermal layer. But on top of the epidermal layer, we have this roundabout 20 micrometer stratum corneum, so the dead cell area. If we could manage to stop the light, the UVC light, already in this dead cell area, it would be a big advantage, because in this case, we can use the disinfection advantage of UVC light while people are present in the room. So let's have a look at the penetration depths of different wavelengths. Here you can see the wavelengths, and here the depths of the human skin and the transmission. So again, for 255 nanometers roundabout, you can see this curve. We have a penetration depth of roundabout 60 micrometer, so coming into the epidermal layer. But if you look at around about 220 nanometers, you can see here the penetration depth is only around about 7 micrometers, which is just within the dead cell area. And if you are exploring this a little bit closer, you can come to a safe zone UVC light, which is limited by 230 nanometers. So something between 200 nanometers and 230 nanometers will be completely stopped. Also below 200 nanometers, but unfortunately, the energy of the photons is already set high that they are generating ozone in the air, and which ozone, of course, is also dangerous for humans. So we are limited to this safe zone, 200 nanometers to 230 nanometers. Now we have to find a light source which is suitable for this area. And we find that the excimer lamp with krypton chloride is very well suited. You can see here the spectrum of this krypton chloride excimer lamp. Here wavelengths 200 nanometer, 250 nanometers. And you can see the dominant peak here is exactly at 222 nanometers. It's perfectly fitting into the safe zone, this green area here, but unfortunately still you have a harmful band. Some emissions of this lamp coming down to 260, 280 nanometers. So still this lamp contains some harmful radiation. So now is the question how we can rid of it. And the solution is demonstrated by Columbia University several years ago. They have a patent on that, and USHIO has the worldwide exclusive license for this technology. You can see again the spectrum again. So in red, you can see here the spectrum with the dominant peak at 222 nanometers and the harmful radiation. And if you apply the special bandpass filter, you can see we result in a spectrum like in the blue shape here, still the dominant peak, but no more dangerous radiation. So again, if you look here in the cross-sectional view of human skin, and the 222 nanometers will be completely stopped in the dead cell area. And this is also verified that this radiation is not dangerous to humans by a lot of experiments in labs and with also human volunteers. Also, it does not cause any eye damages. As you can see here, also cross-sectional view for the eye, the cornea, the lens, and you can see here the UV transmission curve of the light going through the cornea. And you can see here in red with 254 nanometer, still a significant amount of radiation is passing through the cornea into the lens and causing cataracts. While with 222 nanometers, here's the screen bar, you can see, so the amount of radiation can be neglected. So also Care222 light is fully absorbed in the cornea and does not affect the lens. So it's also safe for human eyes. So here I want to show you what we are providing to our customers. So mainly right now in Europe, we are selling these component sets, which is part of it here. We have the lamp with the krypton chlorine lamps. It's 4 inside, and the electronics for ignition of the lamps. And on the right side, you can see also a complete solution, which is currently not available in Europe yet, but maybe in the near future. However, coming to this, I think it's now a good time also to say, please listen to the next talk of our partner Medico, because they are a manufacturer of UV lightings. Thank you very much for your attention, and I now switch back.
Thank you so much, Jörg, for the very interesting and clear presentation. Maybe before to start with the presentation of Nicolas, here we have several end users in the room. So I would like to ask you which application you are targeting. You showed the example of hospitals, but in your opinion, which are the other potential users of these technologies? And
there are too many to name, right? But okay, the easiest way to understand is to use it, for example, in an office. So everywhere in an office, or of course in waiting rooms. So anywhere where people are present. So this means, yeah, all over where people are. So it's, I think.
Okay, yeah. So this technology is addressing more or less the room populated by people. So this is
exactly, yes.
So this is really a lightning support for the disinfection of these environments.
Yes,
okay.
Correct.
So I'm just checking. There is anybody from the participant that has a specific question on this presentation? I see. I'm just scrolling. Which are the?
Yes, there is one question in the chat that actually interests me a lot also as well. Yeah. So you're speaking about the 222 nanometer wavelength, which seems to be okay for the skin, but how about the eye safety?
Yeah, this I mentioned before. So the eye safety is also confirmed that the light is not passing through the cornea. Oh. So I think this is a topic maybe which Nicolas Volet will talk about. So ACGIH in US, they just increased their proposed threshold values for this radiation, so significantly. So, but I think it is a topic maybe for the next presentation.
Okay, so maybe we can proceed with the next presentation of Nicolas. Because here with Nicolas from UV Medico, we will have a concrete application of this technology. So maybe we will also have more to ask and to understand.
All right. Hi, everybody. Can you see my screen?
Yes, sure.
My name is Nicolas Volet. I'm the co-founder and CTO of UV Medico. I'm also the head of a research group of photonics at the Department of Electrical and Computer Engineering of Aarhus University and a board member of the Danish Optical Society. Our headquarters is in Aarhus, which is the second largest city in Denmark, right here in the Jutland Peninsula. The picture on the right shows a view of this beautiful city with the university campus in front and the harbor in the background. I'd like to start by thanking EPIC for the organization of this meeting and the invitation to talk today. As Dr. Jörg Söllner mentioned, we are partners with USHIO, and we acknowledge support from Innovation Fund Denmark. I divided my talk into 3 parts: the present with our current products and activities, the past. A lot of people have worked in some aspect of far UVCs for many years. Therefore, I'll give a short historical summary of some of the major discoveries and their implications, in particular with respect to regulations. I'll end my talk with a few words about our upcoming activities. We started this company with the mission of fighting the spread of infectious diseases with human-safe UV light. Some of our current projects involve the protection of sport teams. This example was with the European Handball Championship, which ended yesterday. 10 of our lamps were installed at the dressing rooms of the Danish team at the MVM Dome in Budapest. During this championship, there has been many cases of COVID among players every day, with one noticeable exception, the Danish team. Their trick was revealed by the media last week. It was filtered far UVC lamps. This brings us to our lamp. The emission area in the central part is based on krypton chloride excimer, with the main emission centered at 222 nanometers. An optical filter is placed in front of it to suppress wavelengths longer than 230 nanometers, which would be harmful. We implemented several extra features at UV Medico. There is a motion sensor and a LiDAR, which measure the distance to nearest objects. They are used with our software to determine the appropriate dose and a duty cycle throughout the day to ensure that the lamp is within regulations. In the visible spectral range, a change of wavelength corresponds to a change of color. In the UVC, this influences how safe or how harmful the light is. Some of the most common UVC light sources are the well-known low-pressure mercury vapor discharge lamps with a strong emission at 254 nanometers. These wavelengths, being close to the absorption maximum of nucleic acid, is indeed very efficient for germicidal applications. This old data suggested that wavelengths below 230 nanometers are promising as well, but light sources were not available at that time. It is also well known that the structural units that make up proteins, the amino acids, have a strong absorption maximum in the far UVC. This information is well documented even in textbooks from the 1980s and was reused a quarter of a century later to explain the higher effectiveness of far UVC lamps in deactivating pathogens compared to their 254 nanometer counterparts. Now, how about safety? Well, a few years after that, in the group of Professor David Brenner at Columbia University, the first tests were done on human cells with far UVC light sources, with the in vivo conclusions that no significant skin damage was produced. Similar findings have now been reported by numerous independent research teams. The maximum permissible UV exposure is expressed in terms of threshold limit values, or TLVs, which consider the wavelength dependence of the health effect of UV. They apply to direct exposure to the eye cornea and provide conservative guidelines for skin exposure. The relevant ISO and European standards essentially follow the values prescribed by the ACGIH. These values have not changed much since the 1970s, and I plotted them on this graph. In this sense, the most dangerous wavelengths is 270 nanometers. Going away from these wavelengths, higher doses are permissible. For 222 nanometers, the radiant exposure, or dose, should be smaller than 23 millijoule per square centimeters. Remember this value, it is important for what comes next. Indeed, already 2 years ago, Professor Brenner's group at Columbia University discovered that human coronaviruses could be efficiently deactivated with far UVC lamps at doses way below the TLV. This was further validated by similar reports more recently. This result gave a lot of hope, but also prompted for urgent research to generate more knowledge about the so-called safe spectral range of far UVC. Some of the conclusions were that to be safe, the lamp must have a proper filter to transmit the 222 nanometer light and suppress other unwanted wavelengths. In addition, experimental evidence accumulated to suggest a revision of the TLV regulations for far UVC. A notice of intended change was issued by the ACGIH at the end of 2020, and new TLVs are now in the 2022 edition, which significantly increase for filtered far UVC lamps. Following our mission at UV Medico, we started collaborations with all major hospitals in Denmark. For instance, at Aarhus University Hospital, our lamps are installed in waiting rooms to reduce the risk of contamination between patients, and tests done by the medical doctors recently led to a paper in the Journal of Biomedical Sciences. Beside hospitals, our lamps have made people very happy in hair salons and kept people safe in numerous cafes and restaurants. I am thrilled to announce that more than 100 units are now installed at the European Futsal Championship in the Netherlands to protect 16 teams. Finally, we flew to China to install an extra 40 units for the Olympic Games, which will start in Beijing on Friday. Thank you very much for your attention and stay safe.
Thank you so much, Nicolas. I think that really it's impressive the example that you gave us. So we have concrete solutions to fight, let's say, coronavirus in this contingent time, but also to have, let's say, a more, let's say, future vision also on future situation, and to have a more clean environment. So I just took note of some elements during your presentation. I understood that regulation has been changed. This regulation has been changed all over the world, or is just on part of the world? So what is your needs from the regulation point of view? And then the other question is, which are for also your challenges for future development? On technological side, I saw, for example, that your device is quite complex. There are several other photonics components, LiDAR and so on.
Well, thank you, Antonio, for these questions. I took note from your questions. You started with the regulations. So I mentioned the ACGIH has changed the threshold level values as of earlier this year. This does not mean that all regulations have changed. In particular, the ISO and European regulations historically have followed the ACGIH regulations. But it takes usually time to adjust to this. As of right now, we follow the former regulation of ACGIH, so the current ISO and European regulations, which state clearly that the TLV is 23 millijoule per square centimeter for 222 nanometer lamp. Please, something that is very important to mention here is that this holds for 222 nanometer lamp. And as Jörg mentioned, krypton chloride excimer lamp, as all excimer lamps, have also sidebands, which means that there is emission at other wavelengths, typically longer wavelengths, which are well known to be dangerous for direct exposure to people, right? So this lamp really should be used only when a proper optical filter is in place. Then you mentioned something on our future development. We have a lot of challenges, of course, and opportunities, and that's why we are proud members of EPIC and also the IUVA to work and partner with several companies towards UVC, towards more even miniaturized version of light sources for the far UVC, and in particular to maintain level of quality and make sure that customers are safe with safe wavelengths, but also safe level of dose for this particular wavelengths. And that's why we are very happy also to hear about companies developing new type of detectors, more sensitive detectors for far UVC. Also exciting to hear about packaging or co-packaging companies for optical components that are suitable for far UVC. We also involved in raising awareness about far UVC in Denmark and beyond with, for instance, the Danish Optical Society, which I'm a board member of, and to create a sort of an ecosystem also with local universities to teach and to train people for this technology.
Thank you so much, Nicolas. Ivan.
Antonio, we have a lot of questions.
Yes,
from
sir.
the
Yes,
audience.
go manage the
I
question.
should have continued speaking.
I need to give them a word. So first, there was Leonidas who wanted to ask a question or two.
Hi, yes, thank you. Can you hear me well?
Yes, sir.
Yes.
Okay, very nice presentation, Nicolas. It's very interesting
Thank
when it comes to disinfection when the UV LEDs. I'm from Eurecat from Spain, and we're basically a research technological center testing this type of lamps for disinfection for different clients. And I was wondering, what is typically or normally the microorganism you use for measuring the dose? Because it's interesting that you put several of these lamps, for instance, in the picture you show from the Danish team, sport team, and there were like about four or three around, but depending on the microorganism you use, if it's a bacteria or it's a virus, and I'm wondering what is the type. And additionally, if you have any information, probably you do, but I just would like to know the information regarding to the energy, how the energy is lost versus the distance from the lamp. So if you have a wide space, and then depending on that, you're gonna have several lamps or just one in certain direction and so on. Thank you.
Thank you, Leonidas. Encantado. So I think thank you for your question. I think your first question was concerning the microorganism that we test for our lamp. I have experience in photonics, right? In our company, we have different departments. One of our department is a virologist, Professor Rönnholm, which also works at Aarhus University, which tested already about a year and a half ago, which tested our lamp, UV Medico lamp, directly onto coronaviruses. There is a coronavirus lab here in Aarhus, Denmark, and this lamp have been tested directly on cultures of coronaviruses, depending on the dose, depending on the distance, depending also on, of course, the beam angle. So we develop different lamps which have different beam angle to customize or engineer the dose with respect to the distance, and to make also these lamps more compact, to integrate them into tighter spaces, such as elevators in particular. This brings me to the second question that you were asking me, how the light propagates. I mean, on the physics point of view, it would be following Maxwell's equations. Now, on an engineering point of view, it would be just the inverse of a square law. Right? If you double the distance from the lamp, typically you have 4 times less intensity of light. And I'm not sure if I am frozen or if you can still hear me.
Yeah, we can still hear you, Nicolas.
Okay, good.
Yes, we have also Mark from Seoul Semiconductor, who is very excited about this discussion. He would like to ask you some questions.
Yeah, thank you very much for the presentation. Very interesting. So one of my questions is how these filters are really controlled, because you mentioned that this can have some issues. So how you control that the filter efficiency will be maintained after 10 years, 15 years? So because you are radiating to the people, right? So this creates some concern. So how you control these filters?
So thank you, Mark, for the question. Maybe I could forward this question to Jörg if you are still online. Otherwise, I could take it, of course. Jörg from USHIO.
Yes, I'm here. Do you hear me?
Yes.
Yeah.
Okay. So in general speaking, the lifetime of the lamps is several thousand hours. So we have already measured that the lifetime also of the filters is in the same range. So there you don't need to, we always look everything together. So lamp and filter.
So here I have I don't know if you can hear me, but I have an example of the lamp. So lamp from USHIO and how we integrate it into a fixture with our motion sensor and LiDAR and technology I mentioned. And so it is, of course, a bandpass filter. If the filter is broken, then we can already see it from the eye, but it is not, of course, a fully scientific answer. We measure our lamps, right? We measure the beam profile, we measure the power of each and every single lamp with a goniometer. And this is also where we like to hear more about companies from EPIC that develop instruments that are calibrated for the far UVC and down to 200 nanometers. It is our understanding that to have a measurement of power, you can take a standard photo detector, but to calibrate it and to have it traceable to standards such as NIST, it is quite a challenge. And we are, of course, in discussion already with some of you in the audience on how to best measure and qualify our lamp to follow regulations. And also on the long term, how often do you need to then remeasure these lamps?
One point more here. So what is the lifetime of these luminaires or systems? And what do you say its lifetime? Let's say depreciation of 10% or 20% when you will say this is not valid anymore, right?
Yes, so currently it's about 10,000 hours that I have in mind for the lifetime, which, Jörg, I don't know if you want to also comment on this.
Yes, in this range, that's correct. And if you consider also these several thousand hours, this is not that you turn on the lamp and have it 100% all time, but you have typically, especially to achieve the maximum thresholds, or not to exceed these thresholds, you have a cycle operation. So in fact, these lights currently operate for several years then.
So you turn on and off them.
Yes, exactly.
Okay. Okay, thank you very much.
Sure. And looking forward to connect also offline if you have more questions.
Great. This is what we want in our meeting.
Thank you very much, Nicolas. One quick thing. So apart from the chat in our meeting, there is also questions and answers. That's a separate button that you have at the bottom. So there are also a few questions waiting for you there. If you could maybe reply to them in written.
Okay, I'll work on this now. Thank you very much.
Or maybe I can also suggest that we can also put on the table so we can have all the panelists open to this question. So I see also here in the chat, we have two chats, that there is a question coming from Dane from Camden. Dane, you want to ask yourself the question?
Yeah, sorry, I joined the presentation a little bit late because some meeting intervened, but I caught the back end of it. And obviously 222 is a very interesting technology for me, particularly from the food industry. So our background is applied applications in the food sector. One of the aspects that keeps coming up is the exposure limits, the long-term health and safety. And obviously they've been increased now, and as you discussed, but is this for deliberate exposure or is this accidental exposure? Because I was under the impression that the original stuff was set up for accidental exposure, and now we're deliberately looking to then go to exposures. How does that play with the regulations, and how are people looking at tackling that? And I like the points about the calibration standards, because that one is, yeah, that's an interesting one for me, because the food industry needs something to be calibrated to a fixed standard. So when that one cracks, I'll be very interested in that as well.
All right, thank you, Danny. Should I take this question? Was it for me? I guess. Concerning the TLV, the regulations, the values that I showed were for an average of 8 hours per day with direct exposure to the cornea.
So the regulation now says you can deliberately directly expose them.
Yes.
Okay.
So even in a regular office space, I don't know about you, but I wouldn't stare at the lamp for 8 hours nonstop in average.
Yeah. I appreciate that. I was just trying to get an idea whether it is now the language has changed to deliberate exposure rather than accidental.
Yes. But the point of this regulation, one of the point, of course, of this regulation is not to stare at the lamp for 8 hours straight, I mean, in continuous or in average. It's also to give a guideline, right? Not also a clear separation of what is safe, what is harmful, but a guideline for this. And also to provide conservative values for skin exposure, right? Because quite frankly, of course, the eye is more sensitive than the skin.
Okay,
yes,
thank
true.
you.
I think that here regulation, and this is really a criticity, because on one side we have to be sure about the effectiveness of the disinfection. On the other, we have to see also which is the extreme. The other extreme is too high exposure. So, this is really probably part of the process monitoring. Danny, are you okay, or you have other comments?
No, for me, that's fine. Yeah, it answers sort of my question. It's, yeah, if ISO can catch up now, that'd be great. And the EU side, then yeah, that'll start to open things up a bit more on the European side, which would be good.
Yes, I think that, yeah, the studies also, there is a question about the long-term effect on humans. Clearly, here we are, all of us are, we are exploring new situation under the pressure of the last period, but in general, we are really exploring. Technology is giving us the possibility to work on specific ranges, and also we are exploring, and also we have to change or to evolve with this situation. If there is no other question from the people, I will move on to the next presentation, because we are really going in something that is also connected to your business, Danny. Because here we are speaking. Oh no, I see just a person, Mihail from UVD Robots. Just raise the hands. So.
Yeah, hello everyone. Mihail from UVD Robots, product manager. I've been working in the field of infection prevention control for the last 6 years, and I've been following developments of UVC, specifically the USHIO Bob presented today, and I've been attending also a couple of webinars, also with scholars from Columbia University presenting their latest findings. I think the last one was a couple of weeks ago. And then I think like there is also a thin line between the emerging body of evidence was actually of long-term exposure of both retina and skin. And I'm surprised hearing that there is even a body coming up with a statement that of a deliberate exposure. And I wonder what is this, what is the evidence back up for this, like where the long-term studies. There are also studies from Scotland on skin exposure and also long-term skin exposure and so forth. So I think like the body of literature is consolidating, and this is yet to be confirmed. I absolutely take the standpoint of open discussion in this forum. It's just for the sake of clarity. And then second, I wanted to add with the FIUVC 222 from USHIO, we talk about first surface disinfection or B, air disinfection. And once we have also the installations and also the limits of the law of physics, distance and so forth, I mean, the software must be quite determining the right levels. It must be really how to say, top-notch in order not to expose the surface of skins and so forth. And yeah, I would welcome probably a replica also from my side, given the discussion and so forth. Yeah, thank you.
Great, thank you so much. But also later we will have other speakers that are going deeper in this topic. But okay, now I will give the floor to Olga. Olga from Laser Components. because she's proceeding in this discussion, also giving us some example on other type of UV disinfection that maybe are going more into the industry. Olga, please.
Thank you. I have also one question for Nicolas, but maybe later.
Yeah, I'm still here.
No, please
later
go
on.
ahead.
Yeah, sure.
There is nobody around. We are only this, a small family room. We are all together.
Yeah. We can proceed with the question in an informal part. So let me go through through my presentation.
Olga, you cannot do that. You say you have a question. Now everybody's quite curious about the questions.
This was my idea. Do you see the right screen right now? I hope.
Yes.
So, hello, dear UV disinfection community, and warm welcome to everybody today. Thank you, Antonio. Thank you, Neringa and Ivan, for organizing this event. And thank you for giving me this opportunity to speak. I'm located in headquarters of Laser Components in Germany. As you can see in our company's name, our main focus is on components for laser technology and photonics, including components in UV region. Usually, we develop and produce the components needed in the market ourselves. For the technology and know-how which we do not have in-house, we work together with the best players in the market. Fortunately for UV region, especially for LEDs in UVB and UVC, but also for detection and optical filters, we have excellent partners. Some of them you are going to see in the following minutes. Now, so let me go directly to an impressive example of the disinfection with UV light. Very dangerous bacteria type is Legionella, especially in showers in hospitals or other facilities where long waterways are established. There are very interesting investigations on it done by Ulm University of Applied Science Professor Hessling Group. Thank you for giving up this information. Previous work results found already that Legionella is even more sensitive to UVC light than E. coli, which is usually used for UV disinfection effect tests. Professor Hessling's team has showed a significant reduction of Legionella applying in UVC LED, reduction necessary to prevent Legionella infection during the usage of the shower. It can be achieved even by using one high-power LED operated with a turbine driven by the water flow itself, so no electrical connections are necessary there. The LED emits directly onto the water floor, as you can see in the picture here. The lowest irradiation dose of roughly 1.9 millijoule per square centimeter led to less than 5% surviving bacteria. This is equivalent to log 1 reduction dose of 1.36 millijoule per square centimeter. This is at the lowest irradiation dose. But if the calculation is based on the highest applied irradiation dose of roughly 5.5 millijoule per square centimeter, then the average log reduction dose Legionella becomes around 1.1 millijoule. Peter, sorry to say no, but I don't have much time to speak today about UVT in water, this time only in clear municipal water. So what are the emitting components now, which can be used for UVC disinfection application I have showed before? Here you see the status of the key products of the US manufacturer bulb. On the left side, you see where we are now, and on the right, the roadmap throughout this year. The single chip LED shows with 100 milliwatt per chip at 250 milliamps, assembled in a small 6x6 package, the most effective device available on the market with a Volet-like efficiency of more than 6%. You can see it in the calculation equation in red. it can be driven even at higher current and shows at 350 milliamps, roughly 140 milliwatts per chip. Throughout this year, we expect a more robust chip with longer lifetime and higher optical power. Moreover, bulb is working on 265 nanometer device. The LEDs can be integrated in a different designs on PCB and offer therefore diverse application options already right now. And two pictures on the right side show bulb's own UV disinfection test in water flow, but also in air flow. If you have more questions to those application references, you can come back to me. The LEDs from another of our partners emit at 265 nanometers. Let's memorize the germicidal efficacy, which is best at 265. Photon Wave from Korea offers variety of chip sizes at 5 different wavelengths, and for disinfection, the best germicidal wavelength with 265 nanometer, then 275, and even the mercury lamp matching 255. All 3 wavelengths cover the disinfection curve at best. The table bottom left compares the inactivation effect of both mostly used UVC LED wavelengths, 275 and 265 for 3 bacteria types at 3 doses. 265, of course, shows the best results. For example, E. coli is most often used for water disinfection tests. Here, even at the very low dose of 0.2 millijoule per square centimeter, 265 nanometer reduces the bacteria by more than log 4. It means less than 0.01% of the original bacterial concentration is left. So how many, maybe it is easier with time, how many time do we need for that? Let's take one LED with 105 milliwatts optical power, as you can see in the red circle on the top table left. We will need 0.02 seconds for this dosage of 0.2 millijoule per square centimeter. And if you memorize the experiment of Professor Hessling, the distance there was very close. There we will be necessary only 0.1 second for log 1 reduction of Legionella, according to his publication. So for this time I've done, it was a very short example of an UV disinfection method and small components LEDs usable for it. It was just one application, of course, but there are much more. And we have this famous AP question: what you can do for us and what we can do for you. So what you can do for us, challenge us with your requirements and ideas. And what we can do for you, we will love to support you and solve your problems together with you. Thank you so much.
Thank you so much, Olga. Very interesting. And here, really, we are really going into some another interesting field, water disinfection. And this is really so interesting. Let's say the human body is mainly made by water, so it's the highest, the largest component. So water is really important. And I see already that there are some questions here in the chat. Noam from Seoul, Biosis. I have a lot of small pictures here. So Noam, would you like to ask directly, please?
Yes, Olga, thank you for the presentation. I'm just curious on the specific application of the shower head. What type of flow rates we're talking about? How much water flow?
The standard water flow is 14-15 liters per minute. What is for shower? Yeah.
Yeah.
Of course, for drinking water is a lower water flow.
Okay. But the disinfection results you showed are based on these water flows.
Yes, yes.
Okay. Okay. Thank you.
Welcome.
Okay.
Sorry for my quality. I just read that the quality of my microphone was not so great. Sorry for that.
Okay. So any other question? Or maybe I make a question myself. So here we see also the trend to miniaturization and also, the consumption. The electrical consumption is really part of this miniaturization. So to be integrated in very small devices. Which is your vision, Olga, for this? What could reserve us the future?
Yeah, I mean, what can be smaller than one LED? If we can imagine the same example with a shower head. So I think, of course, if you use something more and filters to filter Legionella or to make them to minimize them somehow else, the shower head could be quite big. And I saw already some in the different trade shows. But if you imagine just one LED, small circuit, and usable with a turbine, so no electrical power, it's very small and it's very usable in such facilities like hospitals or anywhere else where the long waterways are established.
Okay, thank you so much, Olga.
Thank you, Antonio.
One more question from Danny at Campbell BRI.
Yeah, I suppose the only question I've got is a follow-up from the 222 nanometers. It's how are you calibrating these lamp sources? I mean, we're starting to see certain applications coming through, and the challenge I have is how do I make sure that the lamp's calibrated? How do I make sure it's traceable? And are people now generating calibrated sources that you can then use to set calibrations up? Because at the moment, that's the challenge that I think the food industry would need to have in place before they'd even implement the technology. Most of the 254 stuff, you send your sensor off, you get it calibrated, it comes back, they know where they're at. With this, it's a specific wavelength. How are you calibrating to these wavelengths?
Yes, so there is anybody that would like to answer to Danny? So here there is a very important gap. Here we need a calibrated sources and instrumentation to measurements, because this is really important for the evaluation of these tools. There is anybody in the room that would like, that has some solution for this topic? I don't see anybody raising the hands yet. So for the moment, I keep in mind, but I already noted in my book, because this is a key point to go on. I will say, okay, we go on. I'm really proud to introduce the next speaker, Dr. Arthur Kreitenberg. And also I have to say a special thanks to him, because he's connecting from the other side of the world. It's a deep night in Hawaii. And this is really the best that a partner is really loving to join our meeting. So Arthur, the floor is yours, and tell about air and surface contamination and decontamination.
Thank you, Antonio, and thank you for including me as a speaker. It's a great honor. So what I'm going to be talking about today is, it's been very interesting hearing the other speakers. All of these apply to 222, to 265, to 254. I'm going to be talking generally about air and surface contamination and decontamination. So the question is, does surface disinfection even matter? I think that the United States CDC has caused a lot of confusion. In April of 2021, they issued a science brief where they said, look, SARS-CoV-2 exposure is respiratory droplets, and that each contact with a contaminated surface has less than a 1 in 10,000 chance of causing an infection, which raises the question, why bother disinfecting surfaces at all? And here's the reason. It's a concept called secondary aerosolization, described by Volet in 2008, well before COVID, and it can occur for any virus. Now, what it means is that, and these are kind of dust particles, fluorescent particles that are roughly the size of viruses and bacteria. So when they are idle on a surface and they've settled onto typically a horizontal surface, and there's a disturbance, a perturbation, they become airborne again and become infectious again. So in other words, you don't have to lick the surface. There's this secondary aerosolization, which is why it's so important to disinfect surfaces in order to disinfect air. Recently, we've seen, again, evidence of this, Omicron hitting sanitation workers. And if you think about the sanitation worker, they're outdoors. They're not around a lot of people. So why are they getting sick? And it's because the viruses are surviving on people's trash. And as they manipulate those trash, it gets airborne again and is causing them to be sick. Another piece of evidence that just came out last week is a group in Japan looked at the different COVID variants' survival on plastic surfaces. The original strain, a couple of days. The Delta, which of course overtook everything, had a surface survival of 4.75 days. Now you look at Omicron, it has a survival surface of 8 days. Now the fact that the survival on surfaces correlates so well with how contagious in the dominant strain, again, is strong evidence of the need for surface disinfection. So surface disinfection and air disinfection are really close cousins. You can't have one without the other. This is a study we did in our lab on an simulated aircraft cabin, and we looked at these fluorescent particles with an unmasked cough over 1.5 seconds. This was presented at the Aerospace Medical Association meeting last year. And what we found is that for the small particle sizes, it forms this plume, a viral plume that's above the seats and can travel for 2 or 3 rows. But the larger particles, they will settle on horizontal surfaces. And that's really important. So you need to do both. Remember the difference, and this is a key slide here, the difference between air disinfection and surface disinfection, since we're talking to a group of engineers, that air is isotropic, meaning the direction of the UVC application is irrelevant. However, surfaces are what's called anisotropic. So the direction of the UVC application matters, and it matters a lot. This is a real clear example. This meter here, this is the horizontal surface where the aperture is. If you have an overhead lamp and the UV rays are coming right down on it, you're getting 1600 microwatts per centimeter squared, good dose. You take that same lamp, you turn it 90 degrees, so now it's a vertical lamp, same horizontal surface, and you're only getting a reading of 5 microwatts per centimeter squared. Big difference. So now that's a meter. Now I gotta tell you, as a surgeon, I don't care about meter readings, I care about germ kill. And this is a study we did in our lab that showed with a UV hammer on one of our devices with vertical lamps and horizontal surfaces, even at 10 millijoules per centimeter squared, and this is on staff, we should be really getting a really good kill. On a textured surface, not even a 1.5 log kill. On a smooth surface, about a 2 log kill. But if you put those lamps parallel and put them over the surface, and the UV hammer allows you to do that, all of a sudden at that 10 millijoules, and it's true regardless of dose, you're getting a 4.5 log kill, both on textured and on smooth surfaces. No difference smooth and textured, big difference smooth and textured. Now, why is that? This is what we call the canyon wall effect. Imagine walking through a canyon, and when the light is coming from the side at 9 a.m., it's not going to reach the floor of the canyon. At noon, when the sun is overhead, the light does reach the floor of the canyon, it's effective. This is exactly the same thing as what's going on when we're trying to disinfect a textured surface. Now, what do we mean by a textured surface? For example, the Formica has valleys that are 100 microns deep. A virus is only 0.1 micron deep. So if you're 2 meters tall, that's standing in a 2,000 meter deep canyon. There's a study that came out with pulse xenon that showed that it's very effective against SARS-CoV-2, both on hard surface and on N95 respirators. However, they put the test surfaces vertically to be parallel with the lamp. So in other words, they stood it up vertically. The problem is germs land 50 times more likely on a horizontal surface than on a vertical surface. The report was silent on its disinfection capabilities on a horizontal surface where things matter. This is a quick video of what happens when you put the lamps horizontal and very close to the surface and move over the surface with a meter, 25 millijoules per centimeter squared. That's going to get you a 6 log kill of SARS-CoV-2. One of our targets in healthcare is C. diff. That gets you about a 3 log kill of C. diff. So in other words, when you put it close to the surface and horizontal, as we say in America, you kick butt. We're so confident about it. We've issued this UV hammer challenge for any other UV device, 254, 265, 222. If you can kill as many germs or more germs than the UV hammer, Timer will donate $10,000 to the charity of your choice. Bring it on. Happy to answer any questions. Feel free to reach out to me.
Thank you so much, Arthur. This is really, you raise some core questions, how we have to manage these technologies. So I'm really waiting, looking who is want to make some question or comments here. Here I see with so many people. Yes, I think that first of all, I think that the first comment that I see in the chat is that clearly a lot of people were traveling from Europe to US and back for Photonic West. So this is really impacting our daily life, and this is very important. And yeah, there is any comments, any question? Come on.
I'll just challenge Dr. Kreitenberg. He's issuing a $10,000 challenge for anybody that can do as well. We have 45 plus peer-reviewed published studies. I'll give you $10,000 if you can get 45 by the end of, say, the year that show that your product actually works in the real world. So I think it's great that you can do stuff in the lab. The real test is what happens in the real world in hospitals. And the idea of canyon effect, when you're coming straight down, you're missing the side walls of the canyon. So I just want to be completely accurate with everybody. Look at the actual evidence, not what I'll say a great physician who may be slightly misguided says in a meeting like this.
Thank you for that comment. We welcome the challenge. The sidewalls are adequately covered because the device is in motion. And we'll be happy to bring on that challenge. Thank you very much. Appreciate the comment.
Peer-reviewed, published studies, Dr. Kreitenberg. Peer-reviewed, published studies.
Next question, please.
Yes, next question, please. Any other question or challenges? I see the colleagues from Riedel. Just a moment, it's very small. Manfred, please go on, make the question.
Hello, thank you very much for the very interesting talk. Just a question, which light sources you use? Mercury, mercury, low pressure lamps, amalgam lamps, or you use excimer lamps?
Currently, we're using a 254 low pressure mercury. We're really excited about 222, and we're really excited about LEDs. Currently, the low pressure mercury lamps are just putting out the greatest dose of UV and the greatest germ killing power per energy consumed. And we're really excited about the developments that are coming up. And the point of our platform is the platform with the multi-angle and motion.
Mm-hmm.
So right now, mercury is the best and cheapest solution. For example, with the 10,000 hours, our device has 5 lamps, which means that we can swap out all the lamps for $100. Whereas if we were to go to one of the LED systems or some of the other systems after 10,000 hours, it's a much more expensive swap.
Will you think that with excimer technology, you would be able to run much higher powers, much higher power levels? You won't be compete with lifetime in efficiency, but the power per square centimeter irradiation that you can get in the UVC should be significantly higher. It means
correct.
Shorter cleaning time.
Let me make 2 comments to that. One is we're not that big on metering. We're big on germ kill, and we're actually working with a company now to have a biological indicator to measure actual germ kill as opposed to measuring UV, because that's what matters to me as a surgeon.
And then as a physicist, it's just those. It's just those. You get the dose at the right wavelengths and you're done.
Right. But we're not killing physicists, we're killing germs. And that's what really matters. So, you know, the point is that you can't always correlate, because of things like the canyon wall effect, you can't always correlate metering with germ kill. And that's why we're really focusing on germ kill. So what our equation is, because we're battery operated, we want the maximum germ kill per per power into the system. And that's what we're measuring.
So mercury is still the best and will for a long time be the best.
We are really excited about the evolvement with the emerging technologies, but right now we're still using mercury. I agree.
Thank you.
Thank you for the question and for the answer. Somebody else who would like to make questions? Okay, just a moment, because here I see a lot of small icons of you. I see Dane again. Dane, please go ahead.
Yeah, so it's not really a question as such. I would just sort of confirm from Arthur's discussion in the fact that from the food and drink industry, low pressure mercury lamps is it. That's what's in the food industry. And they go for that because it's, like as Arthur said, it's cheap to swap the lamps out. They get the lifetimes that they want. As soon as this technology really starts to challenge that, and I start seeing it from an industrial validation point of view, that's when I know the technology has really caught up from the energy efficiencies, the lifetimes, the outputs, and they've got the right calibration standards and things that you can trace back and calibrate. That's when I think then there'll start to be a real big shift. But low pressure mercury lamps dominates the food and drink industry as we're speaking now.
Okay, yes. I think that also you said a very important keyword, validation. Here really the process validation is a key element to proceed with this technology and to have further implementation of these technologies in industries.
Definitely. I think there are some extra data that's still accumulating and building in the LEDs and the eximers, and I think that mass is gathering, but 254 has been around a long time. There's a lot more data there. There's a lot more confidence there. It just takes time, I think.
Yes, sure. So it's very interesting discussion, and probably really it takes time. And I think that it takes a long time to discuss it, to go deeper in this topic about validation and the certification side. I see no other people raising the hands. So, okay, maybe Manfred, you still have the hands on, but I assume that there are no other questions here. So I would like to go on with another tile of this puzzle, is how to check the dose when we make this irradiation of the surfaces. And here it's interesting to listen to the last speaker of the afternoon. Just a moment, I'm a little lost. Here we have Dane Rönnholm from Intellego. They developed a specific dosimeter, I would say, to check the exposition. So the floor is yours, Dane. Unfortunately, we have some. Okay, is the first slide or?
No, it's not.
It's here.
There it is. Thank you very much, Antonio. Good afternoon to all of you. Welcome to this session. And thanks also to EPIC for inviting me as a speaker. I'm Dane Rönnholm, Sales Director, Europe and Middle East for Intellego Technologies. I have also, in my previous life, a background within autonomous UVC robots, as well as vision and robotics technology. So that is a little bit about me. Next slide, please. Intellego Technologies. Yes, we are a Sweden-based company. We are a company that has the headquarters in Stockholm, and we have the production in the southern part of Sweden. We have a world patent on the photochromic ink and the production process that produces those dosimeters. And we have, of course, also a long background, I would say. Everything is of course, interesting when we talk about long backgrounds, but we started already in 2011. So that was long on before the COVID pandemic. We are not a product out of the COVID pandemic. We started already with the clear intention of providing a tool for accurate, precise, and stable measurement of UVC dosages. And at that time, already were present problems in hospitals with multi-resistant bacteria, for example. And there was a global need for a tool, an easy-to-use dosimeter that could handle those problems and that we could address those problems. We have subsidiaries in China and in United States, and we are a number of global organizations also, of course, within this field. I also want to say that we have the production in Sweden, like I said, but we're also serving the global community, which a large number of you that are listening today are customers to us. So we are serving all these customers out of Sweden. Next slide, please. So how does it work? How does we fit in the supply chain of UVC disinfection? At the top, there is an example of one of our dosimeters. It's the quick check card, it's called. Like I mentioned on the previous slide, we are using a technology which we have a patent for, of course. This card, you see a circle in the middle. The yellow is the starting color. Once this card is exposed to UVC radiation, it will start to change color. We have the color scale from yellow, then in different stages up to deep purple or deep pink, sorry. What is important to say here is that UVC disinfection is a process that is invisible. There has always been a need, and there will always be a need to be able to secure that you have irradiated the right dose to the surface or to the area that you want to expose it for. On the left side, you see two examples, one with the starting color and one with the finishing color. So the card, which is just a few microns thick, can be placed anywhere in a room. It can be placed on a wall because it has an adhesive backside. It can be placed on a chair, table, door, whatever, in order to secure that you have reached all the areas of the room that you wanted to reach. The uniqueness with Intellego's technology is that this card can be modified per wavelength and per energy level. So what you see on the left side, that is just a couple of examples, because the thresholds, the millijoule thresholds can be changed. The design and language and so on, labeling or whatever, can also be changed. So we can define the needs together with the customer, and we can provide you with the dosimeter that fits your needs perfectly well. Next slide, please. We have already said that these cards are taking care of the needs for the UVC disinfection industry. We have a number of different cards. We have a number of different situations where different wavelength is needed. We have conventional 254 nanometers. We have LED UVC 260 to 280, and then we have far UVC 222 nanometer, which we have already heard about. So within all these three categories, we have a number of different products with a different number of thresholds, of course, to be able to serve all these needs. What is happening with all these dosimeters when they are exposed to UVC lights? Yes, we said before they change color, but we want to stress again, it's about the accumulated dosage. So let's pretend we are in a situation we have placed the dosimeter on the wall, for example. You are using, in this case, a robotic solutions as a light source. something happens during the process so that the robot stops before the card has reached the first threshold. So that means the accumulated dosage of, for example, 25 millijoule per centimeter square is not reached. Do you need to replace the card? The answer is no. Nothing will happen with the card until the first threshold has been reached, and then it will change color. And then you continue with the process, and then the next threshold will be even another color. And maybe there is a third threshold also, and that will also have a third color. So once the full capacity of the card is used, so to speak, then you need to replace it. Next slide, please. For Intellego, it's very important also to be backed by international research. For our customers, it's very important, and for us also. I mean, here is just 3 examples of institutes that have evaluated our products. We have the Berkeley, we have the Case Western and Reserve, and we have the RISE Institute in Sweden. These are all well-known and world-known authorities on this field. And they have stated that we have the most stable and most reliable and most secure dosimeters in the world. We have a full validation package, of course. So if anybody is interested after this session, I'm happy to send out the full validation package showing all the reports and all the studies in its full. So you can read about it and see the level of our security and preciseness and accuracy. Next slide, please. We are active in a number of industries. It's very obvious and it's very mandatory that we would like to be a part of healthcare. We talk about hospitals, we talk about labs, we talk about care homes, we talk about elderly homes, etc. Everywhere where there is a healthcare situation or a healthcare problem. But we are also heavily involved in pharma production. We are involved in food production. We are involved in horticulture, mining, and a number of other industries as well. And one example, just to go a little bit outside the box here, is curing. We have a clear process. We have developed products for curing. And this is really something that is really interesting, because in any case where you want to measure a UVC dosage in UVC disinfection, it's very important that you meet the demands of the disinfection. For example, if you want to reach 25 millijoule per centimeter square in a disinfection process, and if you go further over that, 100 millijoule, 200 millijoule, and so on, that is something that is in some cases not good, because you have problems with underdosing, but you have also problems with overdosing or material degradation. For curing, for example, underdosing is a complete no-go. That can never happen. So it's very important in the curing industry that you at least reached the dosage that you needed to reach. Otherwise, there will be heavy problems in the production process further on. You see a number of different examples, different cards. We have developed many different types, and we can develop many different types for many different situations. Like design can be different. We can add things and remove things, language and so on. And we can also develop exactly the right thresholds that the specific customer or the specific industry needs. Next slide, please. What I also want to mention here is that we have an app system. We have an app system that we have developed, and this app system can be customized depending on the specific customer with specific features, and also with specific functionality and address to a specific situation, application, or industry. It measures the energy exposure and stores the data. Could be in the cloud or could be on another media. Next slide, please. Yes, why Intellego dosimeters? We have already mentioned that we are dealing with an invisible process. So there is a need, visible and accurate proof to avoid overdosing, underdosing, to have a visible proof and evidence that you have reached your goal. We know that in the industry, there is a number of problems or situations you need to handle. The laws of physics, shadowing, repositioning, material degradation, and so on. You all need to be aware of the problems, the situations you need to handle. And there the dosimeters are excellent because you can place them anywhere in the room. You can make sure that you have reached all the areas. You can also see where the problem areas are, and you can see that you have reached the accumulated dosage that you wanted to reach. We talked earlier also during this session about calibration, validation. This is a tool for calibration and validation, dosage measurement, yes, and quality assurance, because a lot of our customers are using this tool in their day-to-day. If you are a producer or if you are a manufacturer, you want to secure that your device is meeting the requirements and the demands that your end customer or the end user is expecting, of course. So you can have this as a tool to validate and calibrate your device before you're sending out it to the customers, and then avoid, of course, unnecessary customer complaints and unnecessary costs. We have also mentioned that you can use it anywhere because it has an adhesive backside. You can take and make notes on it, and it's just a few microns thick, so you can use it in tight spaces, in production lines, and in other places where a normal radiometer, for example, or other type of measuring equipment is impossible to use. It measures the accumulated dosage. That is important. We are about measuring the accumulated dosage, and that can continue even if the irradiation process is interrupted for some reasons. We have the most accurate dosimeter on the market that is backed by recognized international institutes, and it only reacts to UVC light. That is very important to stress. So it's not affected by ambient light or something else. We have a shelf life of 3 years, so our dosimeters can be on the shelf for 3 years. And like I said, we are covering 254, 260 to 280, and 222 nanometers, and also pulse xenon. Our advantage in this presentation was also stressed by saying that we can customize dosimeters to your specific needs. Both when it comes to size, when it comes to design, language, labeling, but also to your specific thresholds when it comes to millijoules. And on top of this, we can also add the app system. So that would be a further layer on top of this that you can use for measuring or storing the results or disinfection rounds. Next slide, please. Questions. I want to stress also that I'm very open to one-on-one sessions. So if you want to email me or call me, you're most welcome to do that. We are happy to set up meetings, online meetings, and go more into details about the functionality and what we can do for you as a customer. And of course, I want also to answer the questions that we got in the beginning, what we can do for you and what we would like in return, so to speak. And again, I want to stress that we can address the interesting challenges you have when it comes to measurement, validation, verification by using our dosimeters. And we would like to be challenged by you with interesting cases from your natural environment and help you solve them, so you can have a more seamless life, a more lean life when it comes to knowing that your equipment are the right ones. They are for sure ready to be sent out to your end users. And if you are an end user in any kind of industry where UVC light is used, we are happy to help you also in your daily life to make sure that you have reached your targets when it comes to either it's UVC disinfection or in other case where you want to use the UVC as your preferable light source. Thank you very much.
Great, great presentation, Dane. I think that this was really interesting to complete this overview of the situation with these cards. And also you raised very important keywords, validation and qualification of processes. So we are really going to the use of these technologies. I see that there is already in hands-on, just a moment, here. Sorry, because here is jumping from one visualization to the other.
Yeah,
I see Ernst from Purdue University. So please, Ernst, go ahead with your question.
Great, thank you. Can you hear me?
Yes.
Great. Thank you for the presentation. I had actually several questions, two of whom are for Dane and perhaps one for Dr. Kreitenberg if there's time that allows. The questions for Dane, first, it seems like you've defined the wavelength dependence of the color change that takes place within this photochromic ink. Is that true? Okay.
Yes.
Great. Then,
yes.
Okay, and is that available?
How do you mean available? The information about it?
Yes.
I mean, we have, like I said, we have world patent on the process about producing our dosimeters, and we have a world patent also for the ink itself, and that these two parts we can't really reveal, but we can reveal all the results around it with our third-party validation package, which I'm happy to share with you.
Okay. Then second one is really a pretty focused question, and that is, have you contemplated the application of this photochromic ink to surfaces? And this really sort of relates to Dr. Kreitenberg's presentation. I'm really thinking about how you might be able to quantify dose delivery to surfaces within, you know, the various textures that exist on these surfaces. Have you contemplated that?
I mean, our dosimeters are used on all types of surfaces.
No, I mean the ink. Let me perhaps bring the distinction that I'm trying to draw here. At least as I understand it, this ink is applied to cards that are then applied to a surface. What I'm thinking about is application of the ink to a surface,
yes,
rather than relying
yes,
on a card. And the benefit of
okay,
applying the ink is that it, depending on how it's applied, it has the potential to give you information about how radiation is delivered to the material within the texture that comprises that material surface. Does that make sense?
Yes, I understand. Yes, and the answer is yes. We have, and we are doing other applications more than just cards, so to speak. So we can apply the ink to other surfaces. Yes.
Great. Thank you.
Great. And okay, my screen, the next one is Nicolas from UV Medico.
Hi there, dear Dane. Thanks for the presentation. Nice to meet you. I had a quick question concerning your dosimeter at 222 nanometers. And my question was, how sensitive is it to wavelengths larger than 230 nanometers, these harmful wavelengths?
Let me answer this. We know that the dosimeters are precise. So we have seen in cases where, for example, somebody has tried to use, if I put it like this, the wrong dosimeter for a certain wavelength. Like in this case, if we take 222 and then you, by coincidence, use a dosimeter for 254 nanometers, there will not be a significant change on that one. So they are very precise.
Are you okay, Nicolas? Or?
But what about the opposite then? If you take a dosimeter at 222 nanometer and shoot light at 254 nanometers, would you see any reading in your dosimeter? Can you discriminate this?
Yeah, I would say we don't see. We have been cross-testing back and forth. They are very precise.
Okay, thank you very much.
Thank you. And I see also Les from LED Matrix that raised the hand. Please go ahead. You are muted. Great.
Okay. Yeah. When one is doing an actual installation with 222 nanometers, you may find that at a surface, you are only getting a very low reading, maybe sometimes in nanojoules per centimeter squared. I see that the sensitivity of the 222 nanometer card is up to 150 millijoules.
Yes.
So how long will it take for somebody working in the field to actually check to see what is being achieved at a surface or at a distance of 2 meters from the light source?
Yeah, I understand your question, and that is a question we sometimes get. And let me first say that the 222 nanometer dosimeter has 5 thresholds. So the first threshold is 20. The second one is 50. Then you have 75, 100, and 150. So you will see something. You will see color change already at 20 millijoule per centimeter square. And when that happened, depending on distance, and so there are many factors depending on how fast in seconds or minutes or whatever it will take to get to that, and that you need to calculate, because if you have the device very close to the dosimeter, it will go faster, of course. If you take it away, laws of physics again, it will take a longer time, for example.
Yeah. Okay, my question is from a practical point of view, when an installation is done, you know, according to my calculations, it's going to take hours for the dosimeter to show the dose even of 20 millijoules. So is there a way to speed that up so that one can actually when an installation is done, somebody can test it within, let's say, a few minutes? And my question is because a lot of the UVC meters use a Hamamatsu sensor. And that's also only allows, I think, up to 5 millijoules. And when you're talking about nanojoules, it takes a long time to get a reading. In fact, with a meter, we can only get a reading maybe 2 to 4 inches away from the source, the 222 eczema source.
No, I completely agree with you, and I mean that is if I compare 2 to 2 nanometer and your question, for example, with the process, if you are using a 254 nanometer source and you expose that one, you expose the card for that light source. It's a matter of seconds before you have the first I would say threshold activated, and then so on and so on and so on. So of course there is a difference, and if with that example you gave me, it will take a long time, indeed. But our technology is that we are calculating the accumulated dosage. So there will be situations where it will go faster, much faster, and it will be situation where it will take a long time, depending on which source you're using, the distance and the time you are irradiating, indeed.
Thank you.
I think that here also Peter Gordon made a very interesting comment in the chat. So Peter, please share with all.
I'm here. I've made 2 observances, but I think with respect to the Intellego discussion, we've been going back and forth in the chat, and fundamentally, I think Dr. Branchley is onto something, right? And we investigate this at the IUVA. In fact, here's a plug for the IUVA food group, because food seem to be really complex services. So I know Danny and I talk about this a lot. We wrote a column and then we started asking questions about, ultimately, can you look at the impingement of optical radiation on complex surfaces, right? So there's the surface, there's reflections, absorbance, scattering, there's the topography of the surface, there's biofilms, and then there's shadowing, right? So this is like Art's thing, right? How do we circumvent all these things? Can we design systems with a little visualization to get to the heart of the matter? And I think that's an invitation to the IUVA, for example, to investigate that in all of us, right? Because Intellego has a paint. I talked about, in a sense, a paint, right? So you have the ability now to sort of impregnate surfaces, whether it's curing or a hospital hard surface or soft surface. Fomites, as aerosols are surfaces, organics and water is a surface, right? I mean, we're on the cusp of actually figuring out how the optical radiation interacts with these complex surfaces. And I think, if that's a takeaway from today's discussion, that's the epic roll, right? We've come upon sort of the thought experiment and then the tools to look into that using physics, photonics, some microbiology, and some material science. So that's sort of where our chat box is going. But thank you for the moment to say that. I think it's a good epic takeaway from our really informative panel today.
Thank you so much. And then I have also Olga raised the hand. Olga, please.
So I have an additional question to the discussion before. Dana, you spoke about the thresholds. Are they limited somehow to time? So I mean, if there is the situation, and as Les also mentioned, if it takes a long time, is it limited that the threshold is not yet reached, and then it will never reach then? So the card, this indicator card, is then will show nothing.
Interesting question. Depending, there are a number of parameters that decides how fast the threshold will change color. I'm holding up now a card here with 2 thresholds. And let me, when I say thresholds, in this case, it's the 50 millijoule threshold and the 100 millijoule threshold. So it's 2 thresholds, and depending on distance, power source, and time, that will together create the result of the color change. and how fast it will go. So if you place, for example, a UVC robot, for example, you place that 5 meters away from the dosimeter card, it will take longer. But it also has a very powerful energy source. If you take another type of equipment which is not that powerful, for example, and you place it also longer from the object. When I say object, this is the dosimeter card, it will take a lot longer. But if you place the light source very close to the object, it will go very fast. And so this card will not stop accumulating the dosage, or even if there's a very low dosage, for example, on a long distance, the card will still continue to calculate the dosage.
And this calculation is not limited somehow for a time?
No.
No. Okay. Thank you very much.
Thank you very much. I don't see any other question here in the room. So I would like to summarize, or try to summarize where we are.
Antonio.
Yes, sir.
Just one quick thing. I want to remind everyone that we're also live on YouTube, and we apparently have one question coming even from YouTube.
Go.
Elise is asking if what is the regulatory recognition of your dosimetry proposal and certification?
Please, can you repeat that question again?
Right. So the question is if your dosimeters are certified, if they comply to the regulations in the European Union or wherever else.
Yeah. I will sort it out. We are not a medical device. We are not under the laws or restrictions of being certified as a medical device. So there's no need for that. And secondly, we are authorized by RISE, for example, which is the state-owned research and laboratory institute of the government of Sweden, and a number of other institutes as well. So we are certified by them. And I'm happy to send out all the reports we have, but there's no need to be certified, for example, as a medical device in the European Union.
Sure. This is not a medical device. Okay. So,
thank you, Dane. Yes, Antonio, you wanted to summarize?
Yes, I prepared a slide just to summarize the situation and the things that I catched more. And so we have air and water disinfection ready at different wavelengths. So we have 222, 254, and also between 260 and 280 nanometer. There is a rising interest, especially for 222, because it's safer for human skin and eyes. The current technology is, by the way, based on lamps and excimer laser, because this is also the practical usage in production lines and in the industry. Clearly, there are incoming laser sources and this wavelength, and especially at 222. Clearly, there are challenges for this application still that we have to face. When we speak about very narrow wavelengths around the 222, from optical point of view, are necessary filters and special optics, because otherwise we learn that unfiltered far UVC can be really dangerous from the point of view of skin cancers and cataract. We are also thinking on production. So this device could be also produced. So we raised 2 times the need to assemble a packaging machine for volume production of this device, as well special optics and special assembly to do it in volumes. It's very important that a concrete need is also about calibration and testing device for UV and far UV, UVC and far UVC. So here we need really to measure, to assess where we are. And last but not least, regulation and validation protocols are not yet frozen. They are evolving. So we are really to follow these. So here is the current situation. Before to go on, I want really to thank all the participants and all the panelists. And I would like really to name all these panelists. Peter Gordon, Jörg Söllner, Nicolas Volet, Olga Stroh-Vasenev, Arthur Kreitenberg, and Dane Rönnholm, that really helped so much to go into this topic and really to make a very good technical discussion. So at this point, I have nothing more to add, just the people that would like to remain, we are all here in, we will remain in the Zoom room, but the public meeting is closing now. And really, I thank you, everybody, and I wish you a great evening. Bye-bye, everyone.
Thank you very much.
Thank you, Antonio. Thank you all.
Thank you.
Oh, I have not a guy like, like Jose, but okay. I'm